In yesterday's lecture, I gave some kind of general overview of some of the topics we're going to consider and explain some kind of basic results about the behavior of integral points on curves under étale morphisms, which were used, or a variant of which, actually, sort of refinement of which was used by Hugo Chapdelaine in his afternoon lecture to discuss some qualitative features of the behavior of the generalized Fermat equation, which we saw, even though it's not a curve, behaves very much like, if, for example, it obeys the same kind of fundamental trichotomy as I described in the morning lecture on algebraic curves. So today I want to kind of get down to business, so to speak, and prove the theorem of Faltings, which I mentioned in my first lecture. About integral or rational point, the same thing on smooth projective curves of genus at least 2. So the theorem is, so let X be a curve over a number field. So K here is going to be a finite extension of the rationals. So be a smooth projective curve over K, or of genus at least 2, so I'm going to call G the genus. Then the conclusion is that X of K is finite. So I'm talking here about K rational points because I've only given myself a curve over K. I haven't specified an integral model for this curve, but it's going to be useful for very shortly, so I'm going to actually fix from now on a finite set S of places of K such that X has a smooth model over the spectrum of the ring of S integers of K. So customary sometimes to call this, to denote this by another letter like script X or something, but I'll just call it capital X by abusive notation. So I'm going to kind of give myself a model for this curve over an affine open of the spectrum of the ring of integers of K, where this curve has good reduction. So I suppose that basically the curve, I've written down an equation with coefficients in this ring of S integers, where the curve doesn't have any singularities in any of the reductions, modulo any of the primes that are not in S. Okay? And that's, I'll be using later. And, okay, so the proof of this theorem of Faltings proceeds by a series of reductions, where every time one transforms the problem into something else. And each step of the proof is actually very interesting because it gives a perspective on other fundamental questions that arise in the subject. So that's really the sort of the overall structure that I want to stress, rather than the technical, some of the technical ingredients, which I won't have so much time to cover. So I want to really describe a series of reductions. There are actually going to be 5 reductions in all, which every time kind of lead to a transformation of the question. So the first step, the first reduction, is to a question known as the Shafarevich problem. And this is a question that we already had a flavor of, at least, in my first lecture when I spoke about zero-dimensional schemes and stated the theorem of Hermite. So in the last lecture, so the Shafarevich problem, So, okay. So remember in the last lecture, my first lecture yesterday, that I defined this set SHA of OD, which was a set of isomorphism classes of finite flat étale algebras over spec D, and you can think of over spec O, and you can think of this geometrically as being the set of zero-dimensional schemes which in the generic fiber consist of D points and which have good reduction over spec O, because on the level of the coordinate ring, having no nilpotence corresponds to none of the points sort of coming together. So that really in all the special fibers over spec O, they still consist of D disjoint points. So this is sort of zero-dimensional schemes of good reduction and cardinality D up to isomorphism over spec O. Now, you could, of course, ask the same kind of question for higher dimensional varieties or other kind of geometric objects. And that leads to a much more difficult question. So we saw that this is finite. That's a theorem of Hermite. And you might ask whether there are similar finiteness results for isomorphism classes of higher dimensional varieties with good reduction outside a prescribed finite set of places. Okay, so that leads to so I'm going to make the following definition. I'll be interested in this problem for the following classes of geometric objects. The first, which is the key one for this section, is what I'm going to denote by SHA of OMG, which are going to be the isomorphism classes of smooth curves of genus G over the spectrum of O. So isomorphism classes of smooth curves of genus G over spec O. So when I say smooth here, I want to emphasize that I don't just mean that they're non-singular in the generic fiber, but also that if I reduce the equation, that these come with models over O, and if I reduce these equations modulo any prime ideal of O, I still get a smooth curve over the residue field, over the finite fields. Okay, so that's the first kind of object that I'm interested in. Well, we're going to be a key role in Faltings' proof is played by abelian varieties, which are kind of higher dimensional generalizations of elliptic curves, which you've probably encountered already in the lectures so far and last week and so on. So I'm going to denote by SHA of O AG the corresponding collection of isomorphism classes of, but now abelian varieties of dimension G. And then, so this is isomorphism classes. And one can also do something slightly different, namely consider, instead of taking, when one has abelian varieties, well, the morphisms between abelian varieties, there tend to be a lot more in some sense. And in particular, there are what are called isogenies, which are morphisms that are finite to 1 on abelian varieties. And we can, instead of looking at abelian varieties up to isomorphism, which is a sort of finer classification, one can look at them up to isogeny. So we'll look at isogeny classes of abelian varieties of dimension G, of course always which are smooth over O. So this is going to be the set of isogeny classes. And these three sets are going to play a crucial role in my description, at least, of the proof of Faltings' theorem. So isogeny classes of abelian varieties of dimension G over the spectrum of this over this fixed base that I've given myself. Okay, so the basic result, the basic conjecture that was made by Shafarevich is that all these sets are finite. SHA of O dash is finite, but this is kind of a far-reaching generalization of the theorem of Hermite, which I discussed last time, sort of to higher dimensional varieties, either curves or abelian varieties. Okay. Oh, yes. That's a good thing to stress. Yes, K isogeny classes.
It's not the same as
Yeah, but if I take an abelian variety which is k isogeny, if I start with an abelian variety over spec O, and I look at one which is k isogenous to it, it will still have a model over spec O. Yeah, but I guess that's not completely obvious. I mean, but it's a fact. So yeah, you don't require extra bad reduction when you do that. But it's important that the isogeny classes are over k. I mean, so I don't want to. Yes. No, I'm taking just smooth models. Yeah, that's all I need for now. Yes. Okay, so now the basic result that governs this first reduction is a theorem of Kodaira and Parshin, which says that Mordell's conjecture follows from the Shafarevich conjecture for curves. So the Shafarevich conjecture for curves implies Faltings theorem. Well, I should maybe say that I sometimes use the Mordell conjecture for what I called here Faltings theorem. That's maybe a somewhat old-fashioned terminology. Okay, so before it was a proof by a theorem of Faltings, it used to be called the Mordell conjecture. For those of you who are too young to remember that. So, okay, so let me give you a sketch of the proof. So the idea of this is a kind of very, very a priori surprising result, because we're transforming a question about rational points on a single curve, on a single fixed projective curve over a number field, into a question about the collection of curves of some given genus over a fixed base, a spectrum of a ring of S integers of a number of fields. So the idea of the proof, I mean, the key ingredient is what's called the Kodaira-Parshin construction, which to every point in x of k associates an element of SHA O mg for some g, actually, which has nothing to do with this g. So the Kodaira-Parshin construction is a construction which to every point p in x of k constructs a curve which is in fact a finite covering of the curve x, satisfying the following properties. So the key properties are the following. First, that this curve xp, or the map pi is ramified only at the point p. So there's a single, so you've kind of constructed a covering of x, which is not quite unramified, but it has only one ramification point on x, which is this point p that you gave yourself. The second feature of the construction is that the genus of xp is greater than 1 and depends only on x, so to speak, only on x, only on the curve x that I started with. I'm going to call G prime this genus. So it doesn't depend on p, that's the main point. So it's G prime. It has nothing to do with the G, I mean, it's related in some way, but I mean, it is not equal to the genus of the curve x that I started with. And the third property, which is crucial, is that xp is smooth over the spectrum of, so you still have to, I mean, you'll see why when I describe a bit this construction. It's not quite spec O, but it certainly has a smooth model over spec of O where I've inverted 2. So there's going to be, the prime 2 is going to somehow appear in the construction, meaning that possibly this curve could have a bad reduction at 2, but in any case, this curve has good reduction outside a prescribed finite set of places. So, so this is an assignment from x of k to this SHA of O of 1/2 mg prime, right? So this construction gives you a map from x of k to SHA of O of 1/2 mg prime. And then if we can show that this map has finite fibers, which I'll explain shortly, and then the finiteness of this set will imply the finiteness of that one. Okay. So let me just give you a quick description. I mean, there's actually several variants. The key fact to know is that this construction is possible. There are several variants that appear in the literature for the construction of this XP. I'm going to give you one which is rather simple. So, so here's an outline of the construction. So I'll give it first over, well, I'll give it only, in fact, over spec k. So I'll do it over the generic fiber and then kind of wave my hands a little bit to convince you that the construction would extend. It would make sense over spec O, or spec O over half, actually. So we start by considering this curve x. So my goal is to construct a specific covering of x, which depends on p, and has this very special ramification behavior that it's only ramified at p. So I start by embedding the curve x in this Jacobian, which is an abelian variety of dimension g. And one way, actually the universal way, of constructing abelian unramified coverings of the curve x is to consider unramified coverings of the Jacobian, of which there are many. I can take, for example, any multiplication by n map. That gives me an unramified covering of the Jacobian. And here I'm going to take the minimal n. I just take the multiplication by 2 map, which is an unramified covering of degree 2 to the 2g. Okay? And I consider the curve, which I'll call x tilde, which is the pullback of this unramified covering over x, the restriction to x. So okay, so now I've constructed, so this x tilde over x is an unramified covering of degree 2 to the 2g. But it's not what I want, because I want something which knows about p. Okay? So I do a further thing. So I am going to let, so I don't know, what do I want to call this map? Yeah, okay, here I don't want to call this pi, I'll call it pi sub p to emphasize the fact that it depends on p. Okay? So here I'm going to call this unramified map pi, and let me denote by pi inverse of p. I'll write pi inverse of p as p tilde plus d, where d is an effective divisor of degree 2 to the 2g minus 1. Okay, so I single out a p tilde. This p tilde is going to belong to x of k. So for this I have to say something. I mean, you see this embedding of x in its Jacobian is by no means unique. It depends on a choice of base point, and the base point I choose, of course, is the point p. So this embedding is the one which sends the point q to the equivalence class of the degree 0 divisor q minus p. The degree 0 divisor up to principal divisors. Okay? So this is the map that this is how I've chosen to embed x in its Jacobian. And then if I look at the inverse image of p, well, there's going to be one point in this Jacobian which is rational over k to make the identity element. Okay? And I take the point p tilde which corresponds to the identity element. So that one is sort of a nice God-given lift to the set of k rational points, and then I look at this remaining inverse image is some divisor which is k rational, although it's a sort of a sum of this many points. The individual points that appear in the divisor are not necessarily defined over k, but the collection of these points is k rational. Okay, so in x tilde, what did I say? Yes, x, absolutely, x tilde of k.
Suppose you have a rational point on the curve, it equals the section and the model. We can remove the points of that section and also the singular points of the back.
Yes.
And then we can choose some vibration of these over the base with respect of O. And I think that it is uniquely determined that section. Doesn't it work?
So why would you do this? No. So what? I mean, okay. So you say that I don't understand the question. I mean, you're.
Suppose that we have a section of the model.
Yes. So I have a point P and x of k. I can extend it to a section over spec O. Okay.
Then we remove all the points of that section, 1 point from each wire.
Yes.
And also the singular points of that wire.
Yes.
Then it will be a surface of negative Euler characteristic.
Yes.
And we can find a finite covering of this curve.
Yes.
Projective. And I think that this
Well, not projective, because
It's not complete.
if you've removed some points.
yeah, but
Oh, on the special fibers only, you're removing points.
we can the universal covering of this will be the upper half plane.
Mm-hmm.
And if we can find, I think we can find some finite covering with this universal covering, and then it will be a projective covering with fibers or curves of units greater than 1. And if this covering determines uniquely that section, then it will help us.
So you're describing me maybe some other variant of the Kodaira part? It's possible. It's possible that something like that would work. But maybe let's talk about it after after my lecture. So definitely we can discuss that. Yeah. I mean, there are, as I said, several variants of this construction which appear, and one actually also works with fibrations. That might be what that has the flavor of what you're alluding to somehow. So okay, so here so I'm going to let the J d tilde. So I want a kind of variety which plays the role of a Jacobian, but allows me to construct coverings which are ramified at certain points, certain divisors. So I'm going to look for the analog of a Jacobian whose étale covers or isogenies classify coverings ramified at D, at this divisor. And that has a name. It's called the generalized Jacobian of x tilde D. And I'll just give you a kind of description of this variety in terms of what it describes. So in terms of its L rational points for some finite extension of K. J tilde of L corresponds to the set of L rational divisors of degree 0 on x tilde. So that's sort of like the description one has for the usual Jacobian. One considers these modulo principal divisors not arbitrary principal divisors, but divisors of the form div of f with the property that f of d prime is equal to 1 for all d prime of degree 0 supported on the divisor d. Okay? So that's sort of the description of this set of L rational points. So it's actually an extension of the usual Jacobian, the Jacobian of x tilde, is a quotient of this generalized Jacobian jd tilde, and the kernel is 2 to the 2g minus 2 copies of the multiplicative group. So there's an exact sequence like that, which is an exact sequence of algebraic groups over spec k, over k. So yes, that's a good point. Supported outside D. I mean, if you have an irrational divisor, you can always modify it by one of these so that it has support outside D. Yeah. Okay, so and that's not hard to actually see this kind of exact sequence given the description I gave here. Okay, and there's a theory of kind of sort of analogous, a geometric analog of class field theory, which tells you that all abelian covers of this curve x tilde, which are unramified outside D, are basically classified by isogenies group homomorphisms of the generalized Jacobian. So we also can embed x tilde into this jd tilde by sending a point on x tilde to the equivalence class of the divisor q minus p tilde, okay? And then I look at the multiplication by 2 map on jd tilde and take the pullback. And that's the thing, that's the curve I'm going to call xp. So that's the kind of diagram I have. I hope it's not confusing. This is my diagram. Okay. And sort of by construction, this curve xp is ramified only at over x tilde. It's ramified only at the points in D, and since all the points in D map to P, this is you get this behavior of the So okay, so we've constructed a map which I call R1 from x of k to SHA of O of 1/2 mg prime. Okay, so maybe let me just give you an exercise in understanding this construction together with the Riemann-Hurwitz formula, which is to compute g prime. So you'll see that g prime, there's an explicit formula for it, basically depends only on g. Okay, so it's independent, of course, of p, as you would expect from the way I described this construction. Okay, so we have this map R1, and then the key point, of course, is that R1 has finite fibers. Yeah, I mean, when I say this, I'm sort of implying that this construction, which I described over the generic fiber, extends to spec O of a half. The reason for the half is you see the prime 2 is somehow very much involved in the construction. I'm taking coverings of degree 2, and it wouldn't be reasonable to expect that these still maintain good reduction over the primes above 2. Those become generally bad. Okay, so why is this the case, that R1 has finite fibers? That's the theorem of the Francis. Okay, so otherwise, you see, if R1 has, if there were infinitely many P that match to the same curve, that would mean that there would be a curve with infinitely many distinct morphisms. So so the point is that the set of morphisms from Y to X is finite. That's the theorem of the Francis. And if there was an infinite fiber, then there would be infinitely many XPs that would be isomorphic to Y. And so that you would and since these are ramified at these different points, P, you would have infinitely many distinct morphisms from Y to this curve X. So this is true, of course, only if the genus of X is greater or equal to 2. Y is any curve. So Y is any curve. Y, any curve. Actually, I mean, this is over C. I mean, I don't, it's not an arithmetic theorem. It's really a geometric theorem, geometric result. If I have two curves over the complex numbers, then the set of morphisms from one to the other is finite. Okay, so, so this is actually interesting because this is, I mean, this is kind of a simple geometric ingredient in the proof, is the main point where we use the fact that the genus of x is greater or equal to 2. Of course, this is false for genus 1, because it could always translate any morphism by translation by a point on x. I mean, so that's where, well, that's really actually mainly where the Faltings theorem breaks down for curves of genus 1. Okay, so that's the first reduction. So now our goal has changed. Instead of trying to prove the finiteness of x of k, we're going to try to prove the finiteness of this collection of curves of a fixed genus with good reduction outside this fixed finite set of primes. And now we're going to, in fact, reduce the problem still further or modify it still further by working with abelian varieties instead of curves. This turns out to be also very important. Yeah. Yes. No, but I'm using it in a proof by contradiction. I'm supposing that this does not have finite fibers. So that means that there's one curve, which I'm calling y, which is isomorphic to xp for infinitely many p's. And that would mean that this y has infinitely many maps to x, one for each p, right? And these maps are all different because they have different ramification locus. Therefore, okay, so so now I want to describe the second reduction, which is actually less surprising than the first, which is to pass from curves to abelian varieties. Okay, so now I consider a second map, which I'm going to call R2, which is the natural map from SHA of O mg to SHA of O ag, which is given by taking a curve x, or an isomorphism class of curves, over spec O of genus G, and assigning to it, maybe I should call this G prime, I guess, assigning to it the Jacobian. Okay. And again, this map, R2, has finite fibers. That's a consequence of a theorem of Torelli. Torelli theorem that R2 has finite fibers. Well, basically the idea is that you can recover a curve from its Jacobian pretty much. Not quite. You need a little extra piece of data, which is the principal polarization arising from the realization of this abelian variety as a Jacobian of a curve. But then a given abelian variety can only carry finitely many principal polarizations, and that's the content. So up to finite ambiguity given by this, so the point is that y is, so x, maybe let me call this y, because I don't want to confuse with the curve x that I had before, that I started with. So y is determined by its Jacobian together with the data of the principal polarization. Okay. And if you don't know what that means, don't worry. It's a sort of a technical point. It's enough to know for what I'm saying that really you don't lose too much information in passing from the curve to its Jacobian. Okay, I don't. This is one technicality which I won't have time to discuss in these lectures. So, is the rather important role played by the polarizations in these arguments. Okay. So that's actually all I wanted to say about the second reduction. It's not too surprising. In the third stage, we're going to pass from isomorphism classes of abelian varieties to their isogeny classes. That's a fairly natural operation to perform also, but that turns out really to be the heart of the argument of Faltings. I mean, that's where, actually, in fact, all that I've mentioned until now are reductions that are not at all due to Faltings. I think they were known before, but here it is a crucial new ingredient. So the third reduction is to pass to isogeny classes from abelian varieties, isomorphism classes, to isogeny classes. So here we consider the map R3, which I'll call R3, from the set of isomorphism classes of abelian varieties of dimension G prime over spec O to the set. Yeah, okay, so I guess here I've replaced O by, I replaced over half by O. So I've inverted, in this O I've inverted 2, okay? I mean, I don't want to keep carrying this 1/2 along with me. So I consider this map from SHA O AG prime to SHA of O IG prime, the set of isogeny classes, of K isogeny classes of abelian varieties with good reduction over spec O. And then the theorem, which is considerably deeper and is due to Faltings, is that this map has finite fibers. So let A be an abelian variety over K, then there are finitely many isomorphism classes of abelian varieties over K that are K isogenous to this abelian variety A. So the K isogeny class of A is finite. And so that's just another way of saying that this R3 has finite fibers, so that I can reduce the problem of showing finiteness of this to showing finiteness of that one. Okay, this is actually the technical core. This result is the technical heart of Faltings proof. And the main ingredient in this, the key technical ingredient, is the notion of height, the Faltings height. So the key ingredient in the proof is the notion of the Faltings height of an abelian variety. So Faltings defines this height using Arakelov intersection theory and studies its behavior under isogeny. So that's sort of the sort of a simple way of summing up the proof, although the proof is considerably delicate and difficult. So I'll just, of course, this is, in some sense, if you want, you can take this as a black box. I'll say a few words about sort of the overall aspect of the proof, but this will remain largely a black box. This is a piece which I'm not going to go into much detail over, okay, this sort of basic finiteness result for isogeny classes. Let me just say that there are two theorems that Faltings proves, theorem A and theorem B. So the first is that the number, actually, in fact, maybe I'm running a little bit short of time, so I'll maybe skip that part. Yes, but here I don't care. For this statement, I said before that if I have a abelian variety which has a smooth model over spec O, any variety which is K isogenous to it will also have a smooth model. but I don't have to mention that. So it's really a result. If you don't need the models. I mean, for stating the result, it's really a result about abelian varieties over K. Okay. Okay. Now I don't have time, so I won't say anything about this. I'll just sort of. So let's take this as a black box, because I want to get to the next stage of the proof. But okay, the basic idea is that we define this height on abelian varieties, and then show that the height doesn't change. So the height, as like all heights, like all reasonable heights, has the property that the set of abelian varieties of bounded height is finite. And then one studies how this height behaves under isogeny, and if one can show that it doesn't change too much, that the set of values taken on by the height, for example, is finite, then one wins. And that's basically the strategy that Faltings follows. Okay. So this will kind of be a black box in the argument, but this basic finiteness result will be used later. So now we have to show that the set of isogeny classes of abelian varieties with good reduction outside this finite set of places is finite. And now we come to the fourth reduction, which in some sense, to my mind, is one of the most interesting passages in the proof. And that is the passage from isogeny classes, from the problem of studying isogeny classes of abelian varieties over K, to that of studying elatic representations of the Galois group of K. So this is one of the most basic fundamental constructions in arithmetic. We start with an abelian variety. So given A, an abelian variety, over K, we can consider its module of L to the n division points, which as a finite group, this is a finite group, as a group, it's isomorphic to 2G copies of Z mod L to the n Z. But, of course, these points are endowed with the natural action of the Galois group of K. I mean, they're not defined over K. They might be defined over some finite extension. But the Galois group of K permutes these points in a natural way, but it preserves the addition law on the abelian variety, which is an algebraic group law. So it acts linearly on this rank 2G module over ZL to the n. So this comes equipped with an action of GK, which is what I'll use to denote the Galois group of K bar over K. And, okay, so one prefers to work with modules that are non-torsion. So a very useful construction in the subject is to pass to the inverse limit of these L to the n division points as n gets larger and larger. So one defines the Tate module, TL of A, to be the inverse limit under the multiplication by L maps of these modules of L to the n division points. And as an abstract group, a profinite group, this is isomorphic to 2G copies of ZL, of the elatic integers. Again, it's equipped with a natural action of the Galois group of K. And if one wants now, one can even work with vector spaces. One can invert the prime L and define a 2G dimensional QL vector space by simply tensoring this Tate module with QL over ZL. And then one gets this nice 2G dimensional representation of the Galois group of K with elatic coefficients. And this object is sort of key to understanding a lot of properties about the abelian variety. Okay? So I want to sort of describe some of the many structures that this elatic representation possesses, because now we're going to sort of transfer the problem of studying these isogeny classes to that of studying isomorphism classes of these elatic representations. So what are the key features of Okay, so so we have the first observation is that, so VL of A, as I said before, is a 2G dimensional QL vector space equipped with two commuting actions. So we can consider the algebra, which I'll denote E. This will be the QL algebra generated by the K endomorphisms and K of A acting on VL of A. So, of course, there's a geometric action. Any endomorphism of the abelian variety defined over K gives rise to a linear transformation on the Tate module tensor with QL. Okay? And so I take this endomorphism ring and I tensor it with QL. So I look at all QL linear combinations of endomorphisms. So that's E. And the second algebra, the second algebra is what I'm going to call pi, the capital pi. And this capital pi is the Galois action. It's the QL algebra generated by the Galois group of K, acting linearly, as I said before, on this representation. Now, these two actions commute because, of course, any endomorphism defined over K commutes with the action of Gal K bar over K. So we have this nice structure. And, okay, the other thing I should mention, which I maybe should have mentioned before, is that VL of A depends, up to the isomorphism class of the GK module, or this GK representation VL of A, depends only on the isogeny class of the abelian variety A. So it doesn't matter if you take two isogynous abelian varieties, you will get the same representation. That's not hard to see because the isogeny induces a map from the Tate modules with finite co-kernel, and once you tensor with QL, you get an isomorphism. Okay? So you don't see, you don't distinguish between isogynous abelian varieties when you pass to the L-adic representation. So that's why it was somehow useful to be able to, that in making this passage from abelian varieties to isogeny classes, we didn't lose more than a finite amount of information, so that we're still we're still in control somehow. So now, so what we have here is a map, which I'm going to call R4, which maps the set of abelian varieties with good reduction outside some set S to, so via this VL construction, this operation of taking the Tate module and tensoring with QL, it maps it to isomorphism classes of 2G dimensional, so 2G prime dimensional, L-adic representations of the Galois group of K. Okay. So now there are two things I want to do. The first is to show that this map has finite fibers. And then, so in other words, that passing from the isogeny class of the abelian variety to this L-adic representation, you actually, in fact, don't lose any information at all. Not only has it finite fibers, it's actually injective. And then the other thing, I would like to show that this set is finite. Now, this is not... Absolutely. In fact, I need to assume more. So I haven't put enough adjectives here, okay? I'm going to have to add a few adjectives to have any hope of showing that this set is finite. Okay? So I'm going to first begin by saying a few words about sort of the basic properties of this L-adic representation, which will allow me to kind of pin down further the image to a set which eventually whose finiteness I'll eventually prove. That'll be in the second lecture tomorrow, in part 2. Okay, so that's the So those are my two goals, which we'll see are actually related. I mean, we're going to kind of tackle both of them at the same time. Well, what can I say about this L-adic representation associated to my abelian variety? I can say a great deal, actually. There's a great deal of structure that's known. Okay, so basic facts. About VL of A. So the first fact is that VL of A is semi-simple. It's a semi-simple representation over E as a representation of the algebra E. In other words, it breaks up as a direct sum of irreducible representations, and so E is a semi-simple QL algebra in particular. So this is a sort of a basic fact about the category of abelian varieties, that if you have a sub-abelian variety, then in the category of abelian varieties up to isogeny, it has a complement. Okay, so yeah. So the category of abelian varieties, sort of up to isogeny, so where you invert isogenies formally if you want, is a semi-simple category, is semi-simple in the sense that all exact sequences are split, right? So that sort of allows you to show that this well, the abelian variety itself would break up into irreducible pieces as a module over the endomorphism ring, and then the same is true for the associated L-adic representation. So we sort of know something about semi-simplicity as a module over E. The second thing that we know about VL of A, is something that Ambrouche was alluding to, is, and that's here where we're using the fact that we're starting from SHA of O. So VL of A is unramified outside outside S, where, okay, what is S here? I didn't use S before, so I guess I can use it now. I mean, so S, where S is the set of all primes which are invertible in O. Okay, so the primes where potentially the abelian variety could be acquiring bad reduction. So if the abelian variety is singular at some place, or it doesn't have a smooth model at some prime, then the Galois representation will typically be ramified. In fact, will be ramified. So those are sort of bad primes. And we also have to include the set of primes that divide the prime L, the prime where because we're taking these L to the end division points, and that those modules typically are ramified at L. So this is sort of the same phenomenon as I had before when I described the Kodaira-Parshin construction. When I was taking these multiplication by 2 maps, I was getting coverings which had bad reduction at 2 typically, and that's the same kind of thing going on here. Okay, so when I take L torsion points, I can't expect to have unramified. But outside this finite set S, which is fixed once and for all, which is finite and doesn't depend on A, I have good reduction. The third basic property of this representation is that it is what is called a rational representation. So VL of A is a rational representation meaning the following. So given a prime V of K, which is not in this set of bad places S, given V not in S, I can consider, so VL of A now is unramified, so I can consider the Frobenius element at the prime V, which is a well-defined conjugacy class in the Galois group of K. So it acts, I mean, it's well-defined up to conjugation, so I get a well-defined conjugacy class of elements acting on this L-adic representation VL of A, and I could certainly look at its characteristic polynomial is well-defined. Doesn't depend on the choice of prime above V or whatever. And so this characteristic polynomial has a characteristic polynomial with coefficients in z of t. So in z of t. So it's a polynomial in t with integer coefficients. And moreover, we can say something about the size of the roots with roots, which I'm going to call alpha 1 up to alpha to g prime, satisfying that the absolute value of these alpha i's, alpha j's, in absolute value is less than the square root of the norm of v, so the cardinality of the residue field of the prime v of k. In particular, I see that the trace of this Frobenius element in absolute value is bounded by 2g prime times the square root of the norm of v. So I have a bound on the trace of this Frobenius element, which depends only on the prime v, on this norm, and I know it's an integer. Okay. In fact, one can say even more about that. I mean, here I made a choice of a prime L, and this characteristic polynomial of Frobenius is independent of L, provided that, of course, L is not equal to 2. Okay, okay. Yeah, I'll raise it here now, because I'm finished with it. So now I've added a few adjectives to my image. Yes, well, no, these two things are, I need less. I mean, these two things are results of they. Okay. This is a sort of the simpler case of Deline's Riemann hypothesis for varieties over finite fields. This is a case of curves. Yeah. Well, these are, of course, serious results. I mean, it's not. Now, okay. So thanks to these three facts, I can sort of pin down the image a little bit, right? Okay. So I can add here unramified outside S, outside S. So this set of primes which are invertible in here together with the primes above L. And I can also add the adjective rational. Rational representations unramified outside S. Okay. I'm still missing one adjective to make the image. I mean, so this is still not a finite set. I'm still missing one adjective. I mean, I don't know if someone can say what I'm missing here. So this set here is still not finite. I mean, it has no reason to be finite. Okay. And let me just. What is it?
Or you assume that?
Yeah. No, that's in the when I said rational, I mean this particular thing, right? With the together with the bounds on the roots. There's something I'm missing.
Not semi-simple now?
Yeah. What is?
A sphere representation.
A what representation?
The missing point is that you have a sphere representation. Simplex.
That's true that I could add this extra piece of information, but it would still not be enough actually to. So it's true that I had this extra structure, this kind of pairing on the Tate module. I'm actually not going to talk about it. I'm not going to need it. It would sort of, you're right, it would kind of make this a bit smaller, but it would still make it finite. The key point is what Ambrosch mentioned, which is semi-simplicity. I still need to know these representations are semi-simple. And so these points here I've glossed over because they sort of are much predating Faltings' proof. But one of the key things that Faltings proved in the course of showing the Mordell conjecture and proving the Mordell conjecture is showing that these analytic representations are actually semi-simple as modules over pi, over the algebra generated by the Galois group. So we had this semi-simplicity over E, which followed from the general theory of abelian varieties. But we have much deeper this fact of semi-simplicity over pi. So I'm just going to state that, and I'll probably end there because I'm running a bit short on time. So this is property 4. So for VL of A is semi-simple as over pi, as a representation for this algebra pi. And this is actually somehow deeper, okay? And I mean, it was proved certainly more recently. This was part of Faltings' proof. So what do I need to do tomorrow to finish the proof, or I mean, to finish my outline, sketch, the modular things I have left out, describing the strategy for proving the Mordell conjecture? Well, there are three things. First, I'm going to explain to you how Faltings shows that the semi-simplicity of VL of A. The second thing I'm going to show is that this assignment, which I called R4, has finite fibers. And it turns out that accomplishing these two things somehow, these two goals are accomplished somehow hand in hand. I mean, some of the same ideas come up in the proof of, one sort of proves both things simultaneously, so to speak. So that's what the first thing I'll do tomorrow. And then finally, okay, now thanks to this, we've added another adjective to our image. So we have that these are semi-simple, pi semi-simple. They break up as a direct sum of irreducible L-adic representations of the Galois group of K. Having added this, we now have enough constraints. This is actually a surprising fact. It was also something that Faltings proved. We've kind of pinned the image down enough that this is actually a finite set. So the last thing I'll show, let me call this set something. I mean, I don't know. I'll give it another name next time. Let me just call it R now, because I want to finish this set R. So I'm going to call this script R. Okay. So this set of representations which I have here is finite.